Good morning. Welcome to AKGEC Digital School. Today's topic is NP completeness. NP completeness is the very important topic in design and analysis of algorithm, which is the very important topic of CSE and IT. So we are going to learn how to distinguish between the NP completeness, NP hard, NP, P. So this is the important topic as well as the research topic. So we are saying that this is the important topic as well as the research topic. How this is the topic is the research topic, we can relate this. We we have studied various problems which I have described in two types, type 1 and type 2. Type 1 problems are those problems which can be solved in polynomial time, and type 2 problems which can be solved in exponential time. For example, like for searching, we have linear search which takes the time n, or we can say order of n. We have another searching algorithm, binary search, which takes the time log n. Another one in sorting, we have insertion sort, which takes the time order of n square or set of n square. We have another merge sort, which complexity is n log n, and matrix multiplication, which complexity is n cube. So we can see that n log n, n square, n log n, and n cube all are in the terms of n. Means these all algorithms are we can say can be solved in the polynomial time. Now we can say we can see in another type, we have 0-1 knapsack problem which can be solved in 2 raised to power n time. TSP, traveling salesman problem, which is also can be solved in 2 raised to power n. Sum of subsets problem, 2 raised to power n. Graph coloring problem, again 2 raised to power n. And Hamiltonian cycle, with again 2 raised to power n. Some of these algorithms may be taken the time n raised to power n, but we have taken the time for all 2 raised to power n in common. NP hard and NP complete problems, we can see linear search is taking time n and binary search is taking time log n. So we have two searching algorithms in which linear search is taking time n and binary search is taking time log n. Means log n is the smaller than n, means we can say that binary search is faster than linear search. But if we want faster than both of the above, if we want any algorithm which will be faster than both of the above, means linear search and binary search, both of them, if any algorithm takes time order of 1 only, if we found any algorithm which takes the order of 1 time for searching an element in an array, for example, then that algorithm will be the faster from linear and binary, both linear search and binary search, both of them. Then 2 raised to power n is much larger than as polynomial time algorithms, for which we have seen that type 2 algorithms which are taking the 2 raised to power n time. So 2 raised to power n is much larger than any polynomial time algorithm. Even n raised to power 10 is much smaller than 2 raised to power n for some large value of n, and n raised to power 100 is smaller than 2 raised to power n for large value of n. Means if we are taking power of n 10, 100, 200, that will be the smaller than 2 raised to power n in some cases or any cases. For example, for algorithms taking exponential time, we require polynomial time algorithms. Means which algorithms taking time to rest power n. We require for that algorithms some polynomial time algorithms, means we require some algorithm that can be solved in polynomial time. And the algorithms taking polynomial time, we want faster algorithms. For example, if linear search is taking time n and log n, binary search is taking time log n, we want faster than both of them, means we want any algorithm which takes only time order of 1. And in the type 2, if some algorithm is taking 2 raised to power n, we want some algorithm for them which takes the polynomial time algorithm, for example n raised to power 100, n raised to power 10, in any of them. That's why it is the research area. That's why it is called research area, means we are searching for faster algorithm for polynomial times, and we are also searching for polynomial time algorithms for exponential time algorithms. Then what is the framework and guidelines for doing research in this area? For NP hard or NP complete, we can see. So there are objective 1 and objective 2. when we try to find the polynomial time algorithm for any exponential time algorithm, then we try to show relationship or association between all the type 2 problems, means all the algorithms which are taking the time 2 raised to power n or n raised to power n, we try to show the some relationship or association between all the types, so that if one problem is solved in polynomial time, then other will be automatically solved in polynomial time also. So this is the first objective. Second objective, if we are unable to write deterministic algorithm for some type 2 problem, if we are trying to write some deterministic algorithm for type 2 problem which can be solved in polynomial time, then why don't we write non-deterministic algorithm for them? And what is the difference between the deterministic and non-deterministic algorithms? Means if polynomial time deterministic algorithm is not possible, then try to write non-deterministic polynomial time algorithm. Means we have only one objective here. We try to find some algorithm which can be solved in polynomial time for type 2 problems which are taking 2 raised to power n complexity. And for them, if we are unable to find any deterministic algorithm for them, then we try to prepare or write any non-deterministic polynomial time algorithm for them. Then what is the difference between the polynomial deterministic algorithm and non-deterministic algorithm? We can see here, deterministic algorithm means if every step or statement working is clear, means how the statement works in that algorithm. If we are having an algorithm and there are number of steps, let's say we are having 10 number of steps, and we are having every step clear, we are having the working of every step is clear, then we can say that this is the deterministic algorithm. If every statement is clear or the working of every statement or step is clear, then we can say that is the deterministic algorithm. And if we don't know how they are working, means if we don't know in any statement in any algorithm which we don't know how the statement is giving some result, then can we write these type of statements? Yes, we can write these type of statements also. It means it contains deterministic steps also, but some steps may be non-deterministic, means it is a combination of deterministic and non-deterministic steps in that type of algorithm. Then when we come to know the type of how the non-deterministic steps are working, then we fill that steps again. This is the then we fill it, means that is the proof of research, and which will be doing later on that step. We can see the algorithm given here. Non-deterministic algorithm for searching algorithm. Here a searching algorithm is given. Algorithm for searching a element in an array A. We try to find total number of elements are n, and we try to find key element from them. Then we try to call a choice statement, and choice statement or a choice function will give some result to j. And next step, we compare key is equal to a of j, means jth is the element in array A, and we are comparing a of j with the key value which we are trying to find. Then we write j if these are equal, and if the condition is satisfied, then we write j, and we say the algorithm is success. And if the algorithm is unable to find the key is equal to a of j, then we write 0 and we write the failure. So here we used 3 non-deterministic things or steps. First is choice, second is success, and number 3 is failure. It means if choice is able to find that element which we are trying to find in that array, that will take only time 1, means constant time. And if this condition is satisfied, then success will also take the time order of 1. And if that is not find out, then failure is also taking the time 1, means all the functions are taking the time constant times, and the whole time will be taken is order of 1. Means this is the non-deterministic algorithm which is for searching a key in an array of n element with the help of 3 non-deterministic features, 3 non-deterministic functions, and which is taking order of 1 time and giving the searching key with success. And if there is not present the key, then it will go to the failure. It means given algorithm for searching a key of array A of size n. Again, here is the same algorithm, array A of size n, and we try to find the value key is present in that array or not. The algorithm takes order of 1 time. It means it is a constant time algorithm. We can see again, if choice, success, and failure takes the time in means taking the time constant time, then the searching algorithm takes the time order of 1 only, means it is the constant time algorithm. It means it will be the faster than binary search that takes the log n time. Means if this type of algorithm is possible, then binary search which is taking the time log n, then this algorithm which is the non-deterministic algorithm because of choice, success, and failure statements, then this will be the faster than binary search which is currently having the faster searching mechanism. It shows a choice element which goes to the key, then we find out, then it is success, means it is have the choice element, and we have to find out the key is equal to that particular choice element which choice has given to jth element. and we then go to the success. And if choice not matched with the key, here in if statement, if A of j is not matched with the key, it fails, means it comes to the failure, means, but it does not means that key is unable to find. Failure, here failure failure doesn't mean that key is not present in, key is unable to find through this method, but it means that search is successful but key is not present in that array. Means choice is that type of feature, that type of procedure in which choice search the whole array only exactly once and try to find the key in constant time only. And if key is not present in that array, then it will come to the failure only, otherwise it will come to the success irrespective of the index. Then if we find out the choice element, which is the most important element in this array, which we have designed for searching non-deterministically, means we don't know how choice is working, we don't know how success is working, no, we don't know how failure is working. So then what is the choice element? And if you try to find the choice element in constant time, that it will become the deterministic. Here we don't know how choice is working, and if we find out the choice how it is working, then it will become the deterministic. But here we don't know how choice is searching the key in exactly the constant time from an array. And if some researcher will give the choice element procedure for the choice element here, then it will become the deterministic someday. But here we don't know how choice is finding element in constant time. Once we fill the choice, then we find the algorithm which takes order of one time. If we don't know, it is magic. Here in this procedure we don't know how choice is working, then if it is successfully searching a key, then it is called a magic only. And when we know, it becomes technique, method or procedure. If some researcher will give the procedure for choice element here, then we replace the choice from that procedure and it will become the techniques, method and procedure. Means it will be deterministic from non-deterministic. And means if we replace the choice element deterministically, then it will become the deterministic algorithm from non-deterministic, which is currently here it is. So how choice is working? We have an array of 6 elements. First element is 10, 8, 6, 9, 4 and 2. If we try to find the key k is equal to 9, and if choice gives me directly 9, I don't know how. So then if choice gives me directly 9, then choice give me directly 9, then j will be the 9 and a of j means array of jth index will be which is the 9 and which will be the match with the key element 9, then write j which is also 9 and then we find the success for the searching that particular element. So today we don't know, maybe tomorrow we know. So today we don't know how choice is working in this statement, in this non-deterministic algorithm. Maybe tomorrow we know the algorithm, the procedure for the same. So today it is non-deterministic, but tomorrow it may be deterministic by some research. It means we can write non-deterministic algorithm for type 2 algorithms too. If we have non-deterministic algorithm for searching an array searching an element in an array, then we can write non-deterministic algorithm for type 2 algorithms also, which can be solved in polynomial time. It means we have two classes, one is P, second is NP. P class means the algorithms which can be solved in polynomial time. NP means which can be solved in polynomial time but non-deterministically. Algorithms in P was in NP earlier, but now they are in P, means we have two classes, P and NP. P is this one. So which algorithms are taking polynomial time in their computations, that may be that were in NP class earlier when they didn't have the algorithm for which is existing now. Means NP is the superclass for P. Means some algorithms which are taking non-deterministic, which are taking polynomial time but non-deterministically, that may be come in polynomial time for after some time, after some days, some years. Means similarly, some which algorithms are taking polynomial times currently that were in NP earlier. It is written here. Algorithm in P was in NP earlier, means that are solved in polynomial time but not deterministically earlier, but now they are in P, means we have deterministic algorithms for finding the polynomial time algorithms in P class. The NP for all type of algorithms which can be solved in polynomial time but with some blank statements. So how we can design these type of algorithms? Means NP class for non-deterministic polynomial algorithms means we have some statements which are some blank statements, means non-deterministically, means we don't know how their statements are working. Means we can write non-deterministic polynomial time algorithm for all exponential time algorithms, means type 2 algorithms, or that algorithms which are taking the complexity 2 raised to power n or n raised to power n or any exponential. So in past we may be working with bubble sort algorithm that takes n square time, but after knowing merge sort we found that time is n log n for sorting some array. So means whichever today is deterministic, yesterday they were non-deterministic, or whichever today are in NP, tomorrow they will become in deterministic. The objective for finding the relationship, we need some base problem. So some base problem, if we have some base problem for type 2 algorithms, then we will be there will it will be easy to find out some non-deterministic algorithm for them. Means objective 1, we are talking about objective 1 of our algorithm, means try to find some relationship between all the type 2 problems. If we try to find some relationship between all the problems which are solved in the exponential times, then how we try to find some relationship? Means for finding relationship we need some base problem. We are talking about satisfiability problem. Satisfiability problem, conjunctive normal form satisfiability problem is the full name of this problem, which takes the proposition calculus formula and takes the time 2 raised to power n, where xi elements are there, x1, x2, x3, where xi can be x1, x2, x3, combination of x1, x2, x3, means we have 3 Boolean values, and conjunctive normal form have the 2 clauses C1 and C2. which joined with the conjunction. Here conjunction is and C1 clause having the x1 or x2 bar or x3 bar. This is C1 clause and this is C2 clause. C2 clause having the values of x1 bar or x2 or x3 bar. So it is taking exponential time. It means it is the same as other type 2 problem. Means we are trying to relate some problem which are similar to other type 2 problems. So here we have satisfiability problem, which is also called CNF satisfiability problem, in which two clauses are there with some conjunction. There are three values. We can have the possible values of xi. We have the values x1, x2, x3. If we try to find the possible values of xi, means x1, x2, x3. So what will be the possible values of xi? The 0, 0, 0, again 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Means total possible values will be 2 raised to power n, means 2 raised to power 3, because n is 3, means total possible values are 8. So means for n variable it will become 2 raised to power n only, means again exponential. Means we can say the satisfiability problem is similar to other type 2 problems. We can show state based tree for satisfiability problem also. If we are here, it means initial step. For that we have two options only. For x1 we have two options, means x1 can be 1 or 0. If we have taken x1 1, after that we have option for x2 either 1 or 0. If we have taken x1 0, then we have option for x2 either 1 or 0. Similarly here, and if we have taken x2 is 1, then we have option x3 for option x3 1 or 0. It means on each level we are deciding some values for another variable. Means here we are deciding the values for x1, here we are deciding the values of x2, and here we are deciding the value of x3. Here we can see also here this is for x1, this is for x1 when x1 is 0, x1 is 1. Then we can show this state based tree like all the type 2 problems which are taking 2 raised to power n. Means we can create the state based tree for all the type 2 problems like this satisfiability problem. Means it is similar to other type 2 problems. If we are able to design the state based tree for any problem, and we can draw this type of tree with some all possibilities like this, then it is similar to, we can say it is similar to the type 2 problem, and which is also taking the time similar time, which is 2 raised to power n. It shows that the satisfiability problem can be solved in polynomial time, and other type 2 problem can be solved in polynomial time. Means satisfiability problem is the similar to other satisfiability problem like this, like from this state based tree and 2 raised to power n complexity. And if we can solve satisfiability problem in polynomial time, then we can say that the other type 2 problem can be solved in the polynomial time. Means we are trying to find some relationship between satisfiability problem and other type 2 problems. Then we can take knapsack 01. If we try to find the knapsack 01 problem, for we can check for the knapsack 01. The similar thing we are trying to find for knapsack 01 problem. We have some profit values 10, 8, 12, we have some weights 5, 4, 3, n is equal to 3, 3 values are given, m is equal to 8, the capacity of knapsack is 8. Then xi, what will be the xi? Means first weight or the first element will be taken, or 1 is taken or 0 is not taken. Second element can be not taken or can be taken. Third element can not be taken or can be taken. Means we have the choice for every element 0 or 1. Means if we have all the choices for, means both the choices for every element, means we are having 0, 1 choice, means having or not having choice for every element, means element 1, element 2, element 3, or the thing 1, thing 2, thing 3, we can say any more thing. The x1, x2, x3 means if we are not taking any of them, if we are taking only x3, if we are taking only x2, x3, similarly we can conclude this up to 2 raised to power 3, means we are having the 3 elements, means similar cases will be there like the satisfiability problem. We can neither have x1, x2, x3, we can have only x3, we can have only x2, we can have only x2, x3, we can have only x1, we can have only x1, x3, we can have only x1, x2, we can have all x1, x2, x3. Means all the similar cases will be like the satisfiability problem. It means it is also same possibilities as satisfiability problem. It is also having the same possibilities like the satisfiability problem. Means also if state-based tree solved, state-based tree, if we design the state-based tree for this type of problem, it will be the same as for the satisfiability problem. And if that state-based tree can be solved in polynomial time, then both the problem, means satisfiability and 0, 1 knapsack, can be solved in polynomial time. Means we are trying to find some procedure if this state-based tree or these type of possibilities which are taking 2 raised to power n complexity, if we are able to find some polynomial time algorithm for this, then we can have the similar thing here also. Then we can find the sum and polynomial time algorithm deterministically or non-deterministically, we can say non-deterministically. Then we can say it can be solved in polynomial time. So it means there is a relationship between satisfiability problem and 0, 1 knapsack problem. So if we are having the some polynomial time algorithm non-deterministically, we can say for satisfiability problem, then we can say 0, 1 knapsack is also can also be solved in polynomial time, we can say in non-deterministically. For example, satisfiability is also taking 2 raised to power n complexity, 0, 1 knapsack is also taking 2 raised to power n complexity, TSP is also taking 2 raised to power n complexity, sum of subsets also taking 2 raised to power n complexity, graphical coloring is also taking, Hamiltonian cycle is also taking 2 raised to power n complexity. Means all these type of problems all are having the same type of problems, same type of possibilities, same type of complexities. But here something is for satisfiability, means satisfiability is NP hard and it is also NP complete. Means we are having some non-deterministic algorithm for satisfiability problem which is already described in algorithm. The satisfiability problem, we can say, we are saying it is NP hard problem. Then again we are coming to next class. What is NP hard? The satisfiability is NP hard is declared in algorithms. NP hard means satisfiability can be reduced in 0-1 knapsack, and 0-1 knapsack is NP hard. We can say if satisfiability can be reduced in 0-1 knapsack means some instance of this and some instance of this I1 and I2. If this can be solved in polynomial time, this can also be solved in polynomial time. Means if satisfiability reduced to some problem L, which is NP hard, and satisfiability reduced to L1, we are taking only L1 in place of L1, L, and L1 reduced to L2, means satisfiability reduced to some problem L or L1, and L1 again reduced to L2. So we have some non-deterministic algorithm for satisfiability problem, which is already there in algorithms, which is already exist. Means we are having non-deterministic algorithm for satisfiability problem. Means satisfiability problem can be reduced to some algorithm L. Means this is NP class problem, which can be reduced to some problem. If some problem can be reduced to another problem, we can say it is NP hard. So we are discovering the new class from NP to NP hard. Means if some problem is can be converted to some another problem, then we can say it is NP hard. And if we are having NP algorithm, mean non-deterministic polynomial time algorithm for them, then we can say it is in NP complete. It means if anyone is solved in polynomial time, then other algorithm will be solved in polynomial time. So L is any problem, means satisfiability can be solved in like L1 problem, can be reduced to L1 problem, and L1 can be reduced to another L2 problem. Means any non-deterministic polynomial time algorithm can be reduced to some problem. It means it is NP hard. Means satisfiability can be reduced to 0-1 knapsack problem, we have seen earlier. The satisfiability can be reduced to some problem L, which is 0-1 knapsack, which is NP hard. So which the algorithms which are taking all the exponential time algorithms, we are saying that those all algorithms are NP hard. And if this algorithm exists for satisfiability problem, means we have already saying that satisfiability is having some non-deterministic algorithm means that will become in the NP complete. Means it means some problem L should be related to satisfiability problem. If we relate some problem L, which can be 0-1 knapsack, which can be TSP, which can be anyone, if we can relate some problem to satisfiability problem, that can be put into NP hard category. And if there is non-deterministic algorithm for that problem, step number 2, if there is non-deterministic algorithm is available for that type of problem, then it comes to the NP complete, which is satisfiability problem. Already we are having these type of classes we have seen till now: P, NP, NP hard, NP complete. Means we earlier having only 2 classes, NP and P. Now we are having 2 another classes also, NP hard and NP complete. Means 0-1 knapsack, graph coloring, all the algorithms which are taking exponential time, we can put these algorithms in NP hard. and NP hard algorithms which can be solved in polynomial time, we can put them in intersection of NP and NP hard, which is here. Means satisfiability problem is having algorithm which can be solved non-deterministically in polynomial time. It means satisfiability problem was earlier in NP hard, but it is currently in NP complete. Means the NP hard type problem which are taking exponential time, but we are having some non-deterministic algorithm for them. It means that these type of algorithms are in NP complete. Means NP hard can be reduced to NP complete day by day, and they the algorithms which are in NP class can be converted to P day by day. Means P class algorithms are increasing day by day, means bigger and bigger day by day, and someday we can say P is equal to NP. Means P class is increasing day by day. Means some problems are directly coming from NP hard to NP complete, then to P class. Means not deterministically, if we find any algorithm for solving that algorithms which are taking exponential times, and if we are having some algorithm for them which can be solved in polynomial time but non-deterministically, we can put it into the NP complete, and when we replace the non-deterministic statement by deterministic steps or statements, then it will become directly to the P. It means P will be the bigger and bigger day by day, and someday we can say P will be equal to NP. This we believe. Means currently P is the subset of NP, and P will be equal to NP, which we believe. It means it is existing, but we don't know how to discover it. Means when we discover it, it will become to P. Means NP class problems all will become to the P. Thank you very much.